Welcome back, students. In this video segment, we're going to take a look at section 2.4, Trig Functions of General Angles. This is a very long section, so you might want to break it down into pieces. Okay, so plan on spending quite a bit of time in video lecture and also an equal amount of time in homework with this section. This is another very large section in the book. It's probably one of the longest sections in our course. Okay, so let's get started with this monster section. There's a problem with the definition of the 6 trig functions that we have so far, and it's a big problem. The problem is they only work for acute angles. We have 6 trig functions that are based on the angle in a right triangle. In this case, the lower left angle theta in the triangle I formed here for us. Now this idea that we have the 6 trig functions restricted to the acute angle theta is a problem because, as I mentioned in the very first lecture of our course, the idea is to be able to apply the trig functions to the mathematics of the sciences. And in the sciences, angles go beyond 90 degrees. They go beyond 360 degrees. And sometimes they're negative. Sometimes they're zero. Sometimes they're actually right angles themselves, and theta, according to the definition that we have so far, has to be somewhere between 0 and pi over 2, or 0 and 90 degrees. So we need to do something. In fact, we need to do something kind of drastic. At first it's drastic, but you'll see it's not really that bad. We need to redefine all 6 trig functions. That's bad news. That's pretty bad news, because we've studied a whole lot of stuff now related to these 6 trig functions as they are. Now, the idea, though, is to redefine the 6 trig functions in a way that's going to preserve most of the work that we've done so far with them. So what I'm going to do is I'm going to try to move the triangle over just a little bit to there. It goes to the right. And this is how we're going to redefine all 6 trig functions. First of all, we're going to take the angle theta, and rather than just putting it in the lower left angle here of this right triangle, we're going to put it in standard position. Okay, so what I'm going to do is put the angle theta in standard position. That means we need an x-axis. It also means we need a y-axis. So far so good. It doesn't look like I've done very much. Well, the next thing I need to do is get rid of the triangle. I need the 6 trig functions to not be based on this triangle with an acute angle theta. Okay, so we're going to do that gently. I'm going to take off the side B, the side B, and I'm going to replace it with a dotted line. So it looks like we're sort of keeping the triangle there. And rather than thinking about A and B as sides of a triangle, we're going to think about A and B as the coordinates of a point. And the point's right here. Okay, and I'm going to extend the line C that contains C to be a ray, so it goes indefinitely. So we kind of have that little triangle here, but A and B are now coordinates of a point. And since A and B are coordinates of a point, I can let theta be equal to 0 or 90 degrees or 180 or whatever. Sometimes I lose the little virtual triangle altogether. If theta were 0, that means B shrinks down to 0, and we lose the triangle. Now, let's redefine all 6 trig functions. And again, I mentioned we were going to do this gently. Instead of calling referring to the side C, we're going to replace it with the distance R from the origin to the point AB. Okay, so far it doesn't look like I've done very much. Instead of calling it C, I'm calling it R. And we're going to redefine all 6 trig functions, replacing that C wherever they occur with R. Look at the sign. It has a C in it. In fact, I'm going to We'll change R to, let's say, a red color here. So sine is B over R. Cosine is not A over C anymore, it's A over R. There's no apparent difference unless you realize that there's really no triangle here. We're only defining the 6 trig functions as they relate to the point A, B, but we still have that little virtual triangle form, little virtual right triangle form. The cosecant and secant follow suit. The C disappears because we're replacing it now with R. What does R remind you of? What does replacing C with R remind you of? It reminds you of a circle. And if you think about it, if you keep the distance R fixed and you let the point AB twirl around and round and round, you generate a circle. Okay. If you're not with me, you will be. It doesn't take long to get used to this. The definitions of the tangent and cotangent don't change. They're still B over A. They're still sort of opposite over adjacent, even though technically we've gotten rid of the triangle. That virtual triangle is still here. Okay? But the angle theta is not restricted to being an acute angle any longer. So let's get used to this. Let's get used to this new definition by taking a look at a specific example. So for example, find the exact value. What does find the exact value mean? It means no calculators, so find the exact, for us, let's find the exact value of each of the 6 trig functions, of each of the 6 trig functions of theta if the point -3, 4 lies on the terminal side of theta. In standard position. I'll just write it this way. Okay. So what's going on here? Let's draw a picture of what's going on here. Okay, first thing we do is draw a set of axes. Okay, so here's the x-axis, here's the y-axis, and here's the point negative. We need the point -3, 4. So -1, -2, -3, 1, 2, 3, 4. So where's the point -3, 4? Let's draw that point. -3, then we go up 4. So there's the point -3, 4. And that point is supposed to lie on the terminal side of theta. Okay, so let's draw the terminal side of theta. Let's draw the angle essentially. So here's the angle. Oops, let me do. Oh, that actually turned out pretty good. I shouldn't redo it. I shouldn't be so picky, but I'm gonna be picky. So here's the ray from the origin, and the point -3, 4 lies on the terminal side of theta. Okay. So in order to do this, we need 3 things. We need an A, an X coordinate, a B, a Y coordinate, and an R. Well, the A is the X coordinate -3. Notice it's not the side of a triangle. That's a coordinate. That's negative. B is 4. So what's R? Well, there is a little virtual triangle formed, and this is a 3, 4, 5 triangle. The Pythagorean theorem will give us 5 for that last side. Once we have all 3 quantities, we're essentially done, just like we were before. The sine of theta, write the 6 trig functions in order. We can even use the SOHCAHTOA device on this virtual triangle. That's going to be very helpful. Okay, so cosecant, secant and cotangent of theta. So the sine is b over r. B is 4, r is 5. You can still use the SOHCAHTOA, so opposite over hypotenuse. The cosine is adjacent, even though it's not a triangle, it's a coordinate. We can think about it as adjacent over hypotenuse. And look at that. Here's the first strange thing that's happening with the trig functions. The trig functions were always positive before. They were always fractional expressions we formed by dividing or creating fractional expressions with sides of a triangle, which are always positive. These are coordinates now, and they don't all have to be positive. The tangent is 4 over negative 3. The other 3 are still the reciprocals of the first 3 in order. So we have the 6 trig functions now where we can have the angles go beyond 90 or beyond pi over 2. They can be negative. They can be actually pi over 2. They can be quadrantal. We couldn't have that before. Okay, so we're going to do a little more practice before we move on with this. So for example, I want to find the exact value of each of the trig functions for the given angle. Let me write that out. Okay, so here's our set of directions for our example. Find the exact value of each of the 6 trig functions of the given angle theta. And the given angle theta in the first example is going to be 210 degrees. I want the sine of 210 degrees, the cosine, the tangent, etc., etc., etc. Okay. The first thing to do is to sketch a graph of the angle in standard position. Okay, so let's sketch the angle 210 degrees in standard position. Well, 210 degrees goes past 180 by how much? By 30. 210 is the same thing as 180 plus 30 more. So let's draw that angle in standard position. 180 plus 30 more. Looks like about right there. 180 plus 30. Oops, that's an ugly looking angle. 180 plus 30 more. So there's the angle theta. So this little angle in here, right here, that's 30 degrees. Okay. Again, why? Because 210 degrees is the same thing as 180 degrees plus 30 more. Okay, well, in order to do this, we need 3 things. We need an x-coordinate A, a y-coordinate B, and an R, a distance from the origin. Okay, so I'm going to construct that point. The point's going to be right here. I have to choose that point. Well, what kind of a triangle is formed here? This is a 30, 60, 90 triangle. And the very convenient sides for a 30, 60, 90 triangle, by now you should know this, are 1, 2, and radical 3. 1, 2, and the medium-sized number is radical 3. What's wrong with this? There's something really wrong with this. What's wrong with this is these are not sides of a triangle, these are coordinates. Okay, so once we have an A, a negative radical 3, a B, a negative 1, and an R 2, it's over. It's over. Now this is hard. This is not efficient. That's kind of a bombshell to drop. This is not an efficient way of getting at these 6 trig functions. There's got to be a better way. There is. We're heading toward that. But we have to start at the very beginning with all this. So I want the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent of 210 degrees. Okay. Well, since I have my drawing, it's a piece of cake. Since with my drawing, this is not an issue. This is not a problem at all. The sine is opposite, sort of the opposite and the hypotenuse still sort of exist here, even though there's no real triangle here. This is a point. A, B is a point. A comma B is a point. But we still see that little triangle, and we can use it. It's a very important little virtual triangle. Again, it's not a triangle. Triangles don't have negative sides. But we're still using it, this virtual triangle, as if there were a triangle. Opposite over adjacent is the tangent. This is 1 over radical 3. I'm going to leave the denominators not rationalized just so we can get through this. The cosecant is -2. The reciprocal of -1/2 is -2. The secant is 2 over negative radical 3. You can pop that negative into the numerator if you want, or you could leave it there. And cotangent is radical 3. Okay. Let's do another one. B. I want the values of the 6 trig functions of, let's say, the angle 90 degrees. 90 degrees. That was unheard of before. Before this, with our previous definition of the 6 trig functions, this was completely unheard of. Can't have a value of the angle theta in a right triangle equal to 90. There's already a 190 degree angle in the triangle. Well, now the definition has nothing to do with an actual triangle anymore. It has the point A, the point B, and the point R. So there's 90 degrees. Where's our triangle? There is no triangle formed. Okay, well, what are we going to do? The terminal side of this angle is the actual y-axis. I need a point. I need a point right there. That's the point AB. There's no triangle formed. Well, what is that point? You can choose any point on the positive y-axis. Be gentle on yourself. The x-coordinate must be 0. The y-coordinate can be anything. What are you going to choose for the y-coordinate? 1. R is the distance from the origin up to the point. So if A is 0 and B is 1, what must R be? The distance from 0 to 1 is 1. And it's over. Well, for the most part, we still have to write out the 6 trig functions. The sine of 90, the cosine of 90 degrees, the tangent of 90 degrees, the cosecant of 90 degrees, the secant of 90 degrees, and the cotangent of 90 degrees. Okay. How are we going to use SOHCAHTOA on this? There's no triangle. Well, it's a little rough when there's no triangle to do that. So we kind of have to remember the definitions. The sine is B, A is 0, B is 1. It's B over R. So it's 1 over 1, or 1. So the sine of 90 is 1. The cosine is A over R, 0 over 1, which is 0. The tangent is B over A. Tangent of 90 is B over A. That's a problem. There's no such thing as 1 over 0. It's undefined. That's another weird thing happening with the trig functions. They're not always defined for angles. And sometimes they're 0. The cosine of 90 degrees is 0. The tangent of 90 degrees is undefined. The cosecant of 90 degrees is 1. The secant is undefined, because 1 over 0 is undefined. The cotangent, well, 1 over 0 is defined, but 0 over 1 is defined. That's 0. Okay, so this is sort of the idea behind this section. The section is much longer. We have a lot of work to do, but the idea is that we can now have theta. We can now have theta equaling angles that go beyond 90 degrees, or equal 90 degrees, or go beyond, and sometimes they can be negative. Let's do one more before moving on here. Let's take a look at the 6 trig functions for 180 degrees. First step, draw a triangle. Or draw the angle, rather. Don't draw a triangle. I'm still hooked on our previous definition. There is no triangle formed again. There is no triangle. That's the angle. The terminal side of the angle is the negative x-axis. We have to find a point A, comma B on that negative x-axis. We can choose any one we want. -1, 0 works just fine. So choose A equals -1, B equals 0. So what's R equal to? The distance from the origin to the point. Very often students will make a mistake with this. The distance from the point 0 to the point -1, 0, the origin to the point -1, 0 is 1. R, for right now, R is positive, so the distance is 1. Okay. Now once we have those three things, A, B, and R, is essentially over. We have the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent of 180 degrees. There's no triangle here for SOHCAHTOA. However, we do have the definitions. The sine of 180 is B over R. 0 over 1 is 0. So the sine of 180 is 0. The cosine of 180 is A over R. So the cosine of 180 is -1. The tangent of 180 is B over A. 0 over anything except for 0 over 0. 0 over anything that's not 0 is 0. So the cosecant is undefined. This cosecant of 180 is undefined. You can't take 1 over 0. The 1 over -1 is still -1. So the secant of 180 is -1. The cotangent of 180 is undefined. Okay, so there's our introduction to this section. It's redefining the values of the 6 trig functions. Now, the fact is, this method takes too long. This method of finding the 6 trig functions values for angles that go beyond 90 or that are not acute, more generally, this is not practical. So for the rest of the section, you're going to learn computational devices, several computational devices for computing the values of the trig functions rapidly, quickly. The idea is to be able to survive in calculus, where you're not going to have access to a graphing calculator or any calculator. A lot of the work, if you have me, it's most of the work. For calculus, you have to be able to access things like the secant of 180 degrees or the tangent of 90 or the sine of 210 very, very quickly. And this is not efficient. So let's work on developing some quick ways of finding the values of the 6 trig functions. The first thing we're going to need is something from our past. We're going to need the chart of special values that I had you guys memorize. The chart of special values. I'll write out the chart just in case you forgot them. The chart of special values gives us the values of the sine and cosine for 0, pi over 6, pi over 4, pi over 3, and pi over 2. Or in degrees, for 0 degrees, 30 degrees, 60 degrees, 90 degrees, and 45 degrees I left out of there. Okay, so the first thing you do is you write sine, and cosine, and the angle. Then you write the angles, 0, We can do degrees for now. 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. This should be in, this should have this by memory right now, by now. You have 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. Then in reverse order we have 1, radical 3 over 2, radical 2 over 2, 1/2, and 0. So this is stuff we have in from our past. And we're basically aiming for the rest of this section at becoming human calculators for calculus. We want to be able to compute the values of the 6 trig functions for certain angles very, very quickly. Like in a situation where you're taking a calculus test. So might as well put in the corresponding angles in radians. In radians we have 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay, so here's our chart of special values. So let's dig into our first method for doing this quickly, this computation of the 6 trig functions quickly for angles. So let's do this. Example, find the sine, let me think of a good angle, 390. 390, the cosine of 390, and the tangent of 390. Well, if we were to do this the way we've done in the last 20 minutes, 25 minutes or so, the first thing to do then would be to draw the angle. Okay, 390 is like going all the way around 360 and then 30 degrees more. So let's draw that terminal side. It's like going all the way around to 360 and then going 30 more degrees. 360 plus 30 more degrees. So there's the angle, 390 degrees. That little extra angle past 360 is very important. That 30 degrees is extremely important in our work. It has a special name. I'm not going to write out the name, but I'll just say it because we're going to talk much more about this angle in a bit. It's called a reference angle. It's extremely, extremely important. The next thing we would do if we were doing this the long way would be to identify the point AB, something comma something, and a distance r. What's a 30, 60, 90 triangle formed here if we allow ourselves to view this virtual triangle? And the sides are in proportion to 1, 2, and radical 3. So we'll use those 3 values. Then it would be over. Sine is 1/2, opposite over hypotenuse. Cosine, radical 3 over 2, adjacent over hypotenuse. Tangent, 1 over radical 3, opposite over adjacent. Now, notice, this is the important thing. Notice that the sine of 390, it's 1/2. But it's the same as if we just looked at the 30 degrees instead of the full angle of 390. This is the same thing as if I just used the sine of 30 degrees. Okay, and the sine of 30 degrees, I don't need the A, the B, and the R. The sine of 30 is on my chart of special values. This is the key. You're seeing the key to this first computational device. If somehow you can replace a large angle or an unfamiliar angle, an angle that's not on the chart of special values, if somehow you can replace the angle that's not on the chart of special, the angle that's not on the chart of special angle values, with an angle that's on the chart, then you go to the chart and pick off the value for the trig function. Instead of looking at 390, all I have to do is look at 30. I can remove that a whole revolution from 390, and it doesn't affect the value of the trig function. That's actually the key. If you remove revolutions, if you remove 360, you don't affect the value of the trig function. If I added another 360, I'd end up in the same place, and I would still have the sine equals to the sine of 30 degrees. Okay, the cosine of 390 is the same thing as the cosine. Well, the angles are somehow related. 390 and 30, they have the same terminal side. That's important, what I just said there. They have the same terminal side. Angles in standard position that have the same terminal side are called coterminal angles. I'll write that out in a minute. In any case, the cosine of 390 is the same thing as the cosine of 30. Just look up cosine of 30 on the chart of special values. It's radical 3 over 2. I'm going to take them off there. I don't need the lengths of these sides. I don't need them, because I have access to the sine and cosine of 30 degrees right off the chart of special values, which we absolutely memorize. The last value, the tangent of 390, is the same thing as the tangent of 30. Well, we don't even have to do that because we know tangent is sine over cosine. It's sine over cosine. This is 1 over radical 3. Okay. Now, we need to make this really, really formal. 390 and 30 are called coterminal angles. Okay, and what that's going to lead to, what we just did, is going to lead to, and this is going to sound like bad news. But remember, I told you there are a lot of these identities to memorize in the course, like 75 or 80 of them or whatever. This is going to lead to 12 more identities, but they're extremely easy to memorize. Okay, they're extremely easy to memorize. Let's get to that. 390 and 30 degrees are called coterminal because they share the same terminal side. One is just bigger than the other. And here's the big fact. This is one of a couple of really big facts. This big fact is actually, in words, those 12 identities that I'm referring to. Trig functions of coterminal angles are equal. That's 12 formulas in that statement. You'll see why. You'll see why in a minute. A few minutes. Okay. I can show you those formulas though, and in other words, in order for me to translate this English sentence, this big fact from English into math, we need to be a little more precise about what we mean by coterminal angles. So here's what we mean by coterminal angles. Let's say an angle, coterminal angles. If the angle is 30, then coterminal angles would be 30 plus 360. If you go all the way around, you end up in the same place. The technical term for that is you have the same terminal side. I could add another 360. So 30 degrees plus 360 times 2. I could add another 360, 30 degrees plus 360 times 3. I could also have, instead of adding 360, I could have subtracted 360. 30 degrees minus 360. I could have subtracted two 360s. Subtract 360 degrees twice. Okay, so if you're not sure about that, let's draw that idea right here. Here's 30 degrees. Here's, let's make the x-axis a little bigger. Here's 30 degrees plus 360. That's the 390 we were talking about. Here's the red angle is, here's 30 degrees minus 360. We end up in the same place. If we add 360s any number of times, say 360 any number of times, or subtract 360 any number of times, we get coterminal angles. I need a formula for all these coterminal angles. We write one formula. Formula for coterminal angles. We write 30 degrees plus 360 times k, where k can be 0. K is 0, we just get 30 degrees. If we have k equal 1, then we're adding one 360. Or two 360s, 360 times 2, or 360 times 3. Or negative 1, 360 times negative 1, which would be subtracting 360, negative 2, negative 3, etc., etc., etc. So when you write something like 30 plus 360k, you are writing a formula for every single coterminal angle with 30 degrees. Now I want to get rid of my drawing here. I want to look at another angle. Suppose we had an angle pi over 4. Coterminal angles would be pi over 4, not plus 360, but plus what? Plus 2 pi. Or pi over 4 plus 2 pi times 2. Or pi over 4 plus 2 pi times 3, etc., etc., etc. Or I could have pi over 4 and subtract one revolution. Or I could take pi over 4 and subtract one revolution twice. That means subtract 2 revolutions, so etc., etc., etc. So the formula for all the angles that are coterminal with pi over 4 would be pi over 4 plus 2 pi k. Now notice I'm not writing where k equals 0 or 1, 2, 3, etc., negative 1, negative 2, negative 3. We assume that when we write this, that k can take on those values. Okay. So, given any angle theta, what do the coterminal angles to theta look like in a formula? Coterminal angles. They would look like theta plus 360 degrees times k in degrees, or theta plus 2 pi k in radians. This is how we express a formula for every single angle that's coterminal with theta, depending on whether theta is in degrees or radians. Now let's return to our mysterious big fact that somehow is supposed to reveal or be hiding 12 formulas. I'm going to restate that again. I want to move that idea down. Okay, so all I did is I cut it and pasted it back down here. So now, this statement, trig functions of coterminal angles are equal, buried in that statement are 12 identities. 12 identities. Okay, they're all in your textbook. I think I wrote in my notes a long time ago that they're on page 144 of the 5th edition, our textbook. So here they are. Here are some of them. This says that the sine of theta plus 360 degrees times k is just the sine of theta. I can remove any number of multiples of 360 degrees, and I don't change the value of the trig functions. Let's look at what I said again. I can remove any number of multiples of 360. 360 times 1, 360 times 2, 360 times k. I can remove that without affecting the value of the trig functions. Trig functions of coterminal angles are equal. There's one. Another one would be secant of, let's say, theta plus 2 pi k is just equal to secant theta. You can remove any number of multiples of one revolution. In this case, in radians, one revolution is 2 pi. So you can remove the 2 pi k's and you get back to the secant. There are 12 of these identities. But there are only 6 trig functions. Why are there 12? For the same reason that we had in similar situations. There are 6 trig functions. We have 6 of the identities look like the first expression, replacing sine with cosine, tangent, cosecant, secant, and cotangent. And we have another 6 in radians. Okay, if you want to see them all listed, they're on page 144. Your job is to memorize them. But all you have to do is memorize the statement. Trig functions of coterminal angles are equal. So what's the basic idea with those 12 identities? Here it is. Suppose we have, and this could be any trig function, I just picked the sine. Suppose we have the sine of a large angle, of the sine of any angle that's not on the chart of special values. What the idea says that we just looked at, that trig functions of coterminal angles are equal, is that we can take the sine of a large angle, and that's going to equal the sine of that same large angle minus enough 360s to get an angle that's on the chart of special values. Then you just pick off the sine from that. If you still don't see it, let's take a look at another one. Let's take a look at an example. Let's take a look at the sine of 405 degrees. So you start the process by asking yourself, is 405 degrees on the chart of special values? And yeah, of course, the answer is no. Well, okay, so subtract enough 360s to hopefully, and that's the potential problem. Sometimes this won't work, but to hopefully end up with an angle that's on the chart of special values. I'm just subtracting 3. Every time you add or subtract 360s, you have a coterminal angle, and the trig functions are unaffected by that. 360 minus 45 is how much? It's 45 actually. And sine of 45 is on the chart of special values. Look up from, or on. Look up. Oops. I pushed the eraser and it didn't work. Okay. Didn't push it hard enough. Look up on chart. Add or subtract enough 360s to get on the chart of special values, if possible. For the next 30 seconds to a minute, it's going to be possible. Okay. We have a little more to go. Sometimes it's not possible, so we have to make an adjustment. Let's take a look at, suppose I want, I'm trying to think of a decent number. Suppose I want the cosine of 750 degrees. So we ask yourself, is 750 degrees on the chart of special values? No. The biggest number on the chart is 90 degrees. So take away 360 from the angle. Oops, and somehow I changed to the sine. Take away 360. Well, 750 take away 360 is 390. Is that number on the chart? No. So take away another 360. So this is equal to cosine of 390 minus 360. You can add or subtract any number of 360s without affecting the value of any of the trig functions. Trig functions of coterminal angles are equal. 390 minus 360 is 30. Cosine of 30 is radical 3 over 2, right off the chart of special values. There's no I drew no triangle, virtual or otherwise. I didn't have to draw the angle. I drew no angle. I drew no triangle. All I did is I used the fact that trig functions of coterminal angles are equal. So how about the tangent of negative 7 pi over 4? So you first ask yourself, is negative 7 pi over 4 on the chart of special values? No. Pi over 4 is, but negative 7 pi over 4 is not. So I'm not going to subtract revolutions. Subtracting revolutions from negative 7 pi over 4 would just make it more negative. I can add multiples of 2 pi. Or I could subtract multiples of 2 pi. I can add multiples of 2 pi. Well, this is a little tricky. What's 2 pi with a denominator of 4? It's 8 pi over 4. 8 over 4 is 2. Negative 7 pi over 4 plus 8 pi over 4 is 1 pi over 4. 1 pi over 4 is on the chart of special values. It's sine of pi over 4 over cosine of pi over 4. The sine of pi over 4 is radical 2 over 2. The cosine of pi over 4 is radical 2 over 2. So the tangent of negative 7 pi over 4 is 1. The idea is you have a trig function. It doesn't matter which trig function. You have a trig function of an angle that's not on the chart. Add a bunch of 360s or 2 pi's, or subtract a bunch of 360s or 2 pi's until you get there. If you do get there on the chart. If you don't get on the chart, that's what the last part of our lecture is based on. So let's see what happens when the process falls apart. This is probably the more involved or complicated part of our lesson, is when this doesn't work. Suppose, for example, I want to find the sine of 240 degrees, the cosine of 240 degrees, and the tangent of 240 degrees. Okay, let's just isolate the sine right now. The sine of 240 is the same thing as the sine of, well, 240 is not on the chart, so I can subtract as many 360s as I want. The problem is, as soon as I subtract my first 360, I go too far. What do I mean by that? I mean I get negative 120. There's no way that I can add or subtract 360s and get on the chart of special values when we start with the angle 240 degrees. That's a problem. That's a big problem. Well, we have a solution to that big problem. That solution is going to require a couple of concepts that are on the side of the solution. So let's take a look at a couple of concepts. The first concept is that of what's called a reference angle. I mentioned that term earlier, reference angle. Reference angles are very simple to understand. There's no real nice formula for them, but it's very simple to understand. I'm going to draw 5 angles, and I'm going to write their reference angles also. So here's our notation. Let theta be an angle, and let's let alpha be this thing called a reference angle, be the reference angle for the angle theta. So what I was about to say is not true. some angles have reference angles, some don't. So if theta is an angle that has a reference angle, I want to let alpha be the reference angle. I'm going to draw 5 angles just so you see, get a visual, without having to look at the definition of a reference angle, get a visual on what a reference angle looks like. The visual gives everything away. So our first angle, suppose our first angle is an angle in quadrant 1. So suppose that's the angle theta. The reference angle is the same. Okay, so in this case, the angle and the reference angle are the same thing. So here's our next example. Oops, I'm going to have to start that one over again. Here's our next example. Here we go. Suppose we have an angle in quadrant 2. And the angle doesn't have to be positive. Suppose that it's this weird angle right here, whose terminal side is in quadrant 2. So that's theta. Okay. It could have been a positive angle, but I wanted to, just for emphasis, that the angles don't have to be positive and they don't have to be between 0 and 1 revolution. The reference angle is this angle. Right away, if you understand these two, or rather these two examples so far, they're sort of giving a pattern for reference angles, even though the pattern is just based on two quadrants. Suppose here's our next angle. Suppose our angle is in quadrant 3. And we can make it just a angle between 0 and 180, or a 0 and 360. So here's the angle theta in quadrant 3. If that's the angle theta, this is the reference angle, alpha. So far we have examples of what a reference angle in quadrant 1 looks like, in quadrant 2, and quadrant 3. I said I was going to draw 5. How can that be, Professor Leon? You're drawing 5 angles, but there's only 4 quadrants. Well, hang on. Here's the angle theta. Let's say this is the angle theta. Here's the reference angle. So if theta is negative or positive, theta could have also been that angle. Theta could also have been the positive angle. It makes no difference whether theta is positive or negative. But the reference angle, whether theta is that negative angle or the positive angle, is alpha. Okay, so here's one more. This last one will almost completely give away what a reference angle is. So let me do that again. So here's our angle. This one. That's theta. It could have just gone directly from the x-axis up to the y-axis, like pi over 2, but I decided I wanted to go around 1 revolution first. And the reference angle? None. There is no reference angle. None. No reference angle. So let's work backwards. What is a reference angle then? What is the reference angle? What do they all have in common except for the last one? They're all what? They're all acute. That means they're all positive angles between 0 and 90 degrees, or 0 and pi over 2. They're all acute angles. Reference angles are always positive, and they never go past 90, and they don't equal 0. They're always look at the one in quadrant 4. If the angle was like negative 30 degrees, the reference angle would be positive 30 degrees. The last thing about reference angle is if the original angle theta is quadrantal, there is no reference angle. Quadrantal angles have no reference angle. There's no such thing as a reference angle for a quadrantal angle. That's a source of loss of points on tests, that students will assume that, well, if the angle is 90 degrees, then the reference angle is also 90 degrees. Nope. Acute angles, or rather quadrantal angles, have no reference angles. Okay, so what are, in words, what is a reference angle in words? So what is a reference angle? Sorry about that. The reference angle for the angle theta, as long as the theta is not quadrantal, okay, the reference angle for a non-quadrantal angle theta it's the acute angle formed by the angle theta and the x-axis. That's the other thing that all those reference angles had in common. They have nothing to do with the y-axis, not at all. They have everything to do with being acute, and they have everything to do with the x-axis being measured either to or from the x-axis. It's sort of the reference angles can be thought of as the acute angle that makes up the difference from the terminal side to the to or from the x-axis. If you missed that, we're going to look at some examples. Examples. Find the reference angle for A. Theta equals 90 degrees. What's the reference angle for 90? None. There's no such thing. 90 degrees is quadrantal. Oops. B. Theta equals negative 45 degrees. What's the reference angle for theta equals negative 45 degrees? Well, here's negative 45 degrees right there. Negative 45 degrees. So what's the reference angle? The reference angle is this angle. So the reference angle is positive 45 degrees. Okay, getting the idea, sort of, I hope, more than sort of. C. What's the reference angle for 135 degrees? Some people are going to be able to see this more quickly than others, but that's okay. 135 degrees. Here's 135. Standard position. So here's the reference angle. It's either measured to or from the x-axis. It makes up the difference from the terminal side of the angle to the x-axis, or from the x-axis. Never to the y-axis. Y-axis has nothing to do with the reference angle. So what is that angle? It's 45. So alpha equals 45 degrees. How do I know? Because 180 minus 180 minus 35 is 45. Okay, how about D? Oops, I keep going back to red. How about I keep doing it again. D. Theta equals 5 pi over 6. What's the reference angle? Oh, let's take a look. This is probably going to be the only part in the course where working with radians is actually easier than with working in degrees. Here's 5 pi over 6. And the reference angle is this little guy in here. What's that angle? It's pi over 6. It's easy. It's easy to find reference angles for angles that have denominators of 4, 3, or 6. 3, 4, or 6. You want to see another one? You see how easy that it is to find the reference angle? Suppose I have theta equals 114 pi over 3. The nice thing, the reference angle is pi over 3. Just knock off the 114. This is what I meant by, this is probably one of the only places in the course where reference angles are easier to find for angles, for some angles measured in radians. So F. Usually radians are the nightmare. How about negative 13 pi over 6? What's the reference angle? You guessed it. Pi over 6. Be careful with that little device. G. What's the reference angle for theta equals 7 pi over 2? It's not 7 pi, it's not pi over 2. Did you get it? None. Every multiple of pi over 2 is quadrantal. Every multiple of pi over 2, oops. Every multiple of pi over 2 is quadrantal. Good grief. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2. There is no reference angle. There is no reference angle. Here's a tricky one. This one tends to get, it's easy, but it's a little tricky unless you pay real close attention to the definition of a reference angle. 89 degrees. What's the reference angle? What's the reference angle? 89 degrees. My goodness, that is so close. So very close. 89 degrees is so very close to 90 degrees. 89 degrees. The number one wrong answer is to say 1 degree. 1 degree would be the angle that between 89 and the y-axis. Reference angles have nothing to do with the y-axis. The reference angle for 89 is 89. What about the one more? What about the reference angle for 91 degrees? Your hint is it's not 1 degree and it's not 91 degrees. So what is it? Gosh. 91 degrees. Just like 89 degrees. Just like 89 degrees, it's really close to the y-axis. Really, really, really close to the y-axis. So this is like 91 degrees right here. 91 degrees. Oops. So this is the reference angle. It's still 89 degrees. So the reference angle has nothing to do with the y-axis, okay? Nothing to do with the y-axis. As long as the angle is not quadrantal, it's going to have a reference angle. Okay, so this was one of the two things we're going to need to handle our little nightmare case of not being able to subtract or add 360s and end up on the chart of special values. We need one more thing. We need one more thing. We need a device. A device. Remember, like SOHCAHTOA was a device for easily coming up with sine, cosine, and tangent. We need a device for or to handle the situation where if you're told that an angle is in quadrant 4, that you should be able to tell whether the trig function is positive or negative. Okay, if you missed that, we need to be able to tell whether a trig function is positive or negative, not by knowing the actual value of the angle, but by knowing just where the angle is, what quadrant the angle is in. So specifically, suppose the angle's in quadrant 1. Suppose the angle's in quadrant 1, 3, 4, 5. All the trig functions are going to be positive for theta. All the trig functions are positive. The sine is 4/5, the cosine is 3/5, the tangent is 3/4. All trig functions. Oh functions are positive in quadrant 1. Okay, what about in quadrant 2? Okay, so with some video magic, here's an example we did about 45 minutes ago. The angle, the problem was find the exact value of each of the trig functions for an angle if negative 3, 4 was on the terminal side of theta. Well, the angle theta is in quadrant 2. Well, which trig functions are positive and which trig functions are negative? The sine and the cosecant are positive and all the rest are negative. Well, we need to be able to do that real quickly. I need to be able to say, ask a question. The angle is in quadrant, or state that the angle is in quadrant 3. Which of the trig functions are positive and which ones are negative? And be able to come up with the answer extremely quickly, right off. Okay, there's a device for doing that. There's a nice device for doing that. I didn't invent this device. This is passed down from student to instructor, instructor to student, etc., etc., etc. So, how to determine which trig functions are positive. Well, it seems like that only answers half the question. It really answers both. The question was, how do we determine whether the trig functions are positive or negative? Well, if I determine that in quadrant 2, the only trig functions that are positive are sine and cosecant, then the rest of them have to be negative. So if I know where the trig functions are positive, or which trig functions are positive, then automatically the other rest of them are negative. So I only need a device to determine, given in a given quadrant, which trig functions are positive. And the device is based on a lie, an absolute lie. And the lie is that all students take calculus. ASTC, all students take calculus. Absolute lie. In reality, a very small percentage of the general population actually ends up taking calculus. Okay. So, how does this device work? This device tells you in which quadrant what trig functions are positive. So how does it work? Well, you assume that the A stands for quadrant 1, S for quadrant 2, T for quadrant 3, C for quadrant 4. So in quadrant 1, all the trig functions are positive. All the trig functions are positive. In quadrant 2, the sine and 1 over the sine, the cosecant, are positive. So the rest are negative. So in quadrant 2, the sine is positive and the cosecant's positive. So what's the tangent in quadrant 2? Well, it's not a sine or a cosecant, so the tangent must be negative. The cotangent must be negative. Right? So if it's not a sine or a cosecant and the angle's in quadrant 2, the trig function will be negative. If it's only sine and cosecant are positive. The device tells you what trig functions are positive. In quadrant 3, what do you think the T stands for? The tangent, and then which other one then? What's 1 over tangent? Cotangent are positive. The rest are negative. In quadrant 4, the cosine's positive, and 1 over the cosine is positive secant, so the rest are negative. Okay, that device for determining what trig functions are positive and what trig functions are negative in a given quadrant, combined with the concept of a reference angle, this is going to allow us to handle the most difficult of the trig function values, namely when you can't add or subtract 360s to get coterminal angles that end up on the chart of special values. Back to 240 degrees. Back to 240 degrees. 240 degrees. Boom, boom, boom. We were looking for the sine, cosine, and tangent of 240. Okay. Well, if we were doing this the absolute long way, like from the very beginning of our lecture, we would graph 240 degrees. 240 degrees is 180 degrees plus how much more? Plus 60. So the angle 240 degrees is like right about there. It's 180 plus 60. Okay. Again, this is how we would have done this at the very beginning. That little extra 60, that's the reference angle. That's the reference angle. Well, all the trig functions are not positive in quadrant 3. Trig functions are not all positive in quadrant 3. If we were going through this business the way we did this in the very beginning, we would need to construct a triangle. This would be a 30, 60, 90 triangle. The sides would be proportional to 1, 2, and radical 3. Okay. So the sine of 240, just from the definition, is equal to opposite over hypotenuse, or b over r, negative radical 3 over 2. The cosine of 240, this is if we did it the long way, the cosine of 240 is negative 1/2, and the tangent of 240, opposite over adjacent, the negatives would cancel and you get positive radical 3. Okay, now compare that with the trig functions of just the reference angle. Remember, the reference angle is acute, so that little reference angle, that's on the chart of special values. The sine of 60 is positive radical 3 over 2. The cosine of 60 is positive 1/2, and the tangent of 60. Trig functions of a reference angles are always positive, all of them, always, 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 always. So we can't make the statement, we cannot make the statement that the sine of 240 is the same thing as the sine of the reference angle. We can't make that statement. What I just drew is false, because the sine of 240 is actually negative, and the sine of a reference angle is always positive. But if you insert a little negative sign there, then it's true. So the trig function of a reference angle, trig functions of an angle are not quite equal to trig functions of reference angle. Sometimes you have to insert a minus sign. The sine of 240 is negative the sine of 60, negative radical 3 over 2. Now look at the cosine of 240. The cosine of 240 and the cosine of the reference angle 60, they're not the same. You have to insert a minus sign. Oops. Equals minus 1/2. What about the tangent? Well, the tangent of 240 actually just equals the tangent of the reference angle. So sometimes the trig function of an angle equals the trig function of the reference angle, and sometimes it doesn't. Sometimes it does and sometimes it doesn't. So when do you have to insert the minus? How do you decide whether you insert the minus or not? Okay, and here's the key. Here's the answer. Here's here's 6 more identities, sort of. let's just look at the sine. The sine of an angle, any angle, big, small, medium size, whatever, except for quadrantal angles. The sine of an angle is almost equal to the sine of the reference angle, except you have to determine whether you insert a plus or minus. And that plus or minus depends on where the angle is. Where is the angle? Okay, so how does it work? How does this work? This last device. This is how it works. The sine of 240. It's going to equal, the sine of 240 is going to equal either plus or minus the sine of its reference angle. The reference angle for 240 is 60 degrees. And that plus or minus is determined by where the angle 240 is. Where is 240? What quadrant? It's in quadrant what? It's in quadrant 3. It's 60 degrees past 180. Okay. Now, so what? In quadrant 3, all students that's the T in all students take calculus. Quadrant 1, quadrant 2, quadrant 3. The tangent and the cotangent are positive. So all the other trig functions are negative. So that says you choose the negative. Then you look up the sine of 60 degrees on the chart of special values. The sine of 60 degrees is radical 3 over 2. So the answer is negative radical 3 over 2. Okay, let's take a look at another one, or the next one. Let's take a look at how we would approach the cosine of 240 degrees. First, you find the reference angle for 240 degrees. Well, it doesn't change. It's still 60 degrees. This is the cosine of 240 degrees is the same thing as the cosine of its reference angle, 60 degrees, with a plus or minus that you have to determine. 240 degrees is still in quadrant 3. Quadrant 1, all. Quadrant 2, students. Quadrant 3, tangent, take. Quadrant 4, calculus. So in quadrant 3, the tangent is positive. And I'm not looking at tangent, I'm looking at cosine. So the cosine must be negative. Then I look up 60 degrees on the chart of special values. And the cosine of 60 degrees is 1/2. So this is negative 1/2. The tangent of 240 is equal to plus or minus the tangent of its reference angle. 240 degrees is still in quadrant 3. In quadrant 3, quadrant 1, all. Quadrant 2, students. Quadrant 3, take, tangent, calculus. In quadrant 4. In quadrant 3, the tangent's positive, and we're looking at the tangent. So we look at positive tangent of 60 degrees. Then this is positive, then sine of 60. Sine of 60 is radical 3 over 2. Cosine of 60 is 1/2. Sine over cosine is radical 3. Okay, if you didn't get this, I'm going to look at one or two more examples of how this works. And it's very easy. It's very easy to use all this stuff, to combine all this stuff. Suppose I want the sine of 5 pi over 4. You can't effectively find this value by subtracting 2 pi, because if you subtract 2 pi, you'll get something negative. So this requires that device. This is going to equal plus or minus the sine of its reference angle. Reference angle for 5 pi over 4 is 1 pi over 4. Then you ask yourself, where is 5 pi over 4? Where is it? It's in quadrant 3. Pi plus pi over 4 is 5 pi over 4. So I'm in quadrant 3. All students take quadrant 3 calculus. In quadrant 3, the tangent's positive. I'm not looking at a tangent. I'm looking at sine. So it's negative sine of pi over 4. The sine of pi over 4 from the chart of special values is radical 2 over 2. So the answer is negative radical 2 over 2. This is an easy device. Okay, let's see if I can do one more here. Let's see. The cosine of 135 degrees. 135 degrees. Okay. First, find the reference angle. We already did this angle earlier. If 135 degrees is that angle, when that angle's in quadrant 2, the reference angle is 45 degrees. So the cosine of 135 is either going to be plus or minus the cosine of its reference angle. And you determine whether it's plus or minus. So 135, where is it? It's in quadrant 2. All students, so S part of all students take calculus, corresponds to quadrant 2. In quadrant 2, the sine is positive. Sine and cosecant are positive. So the cosine must be what? Negative. Look up 45 on the chart of special values. The cosine of 45 is radical 2 over 2. So the answer is negative radical 2 over 2. Okay, this device is not difficult at all. Okay, this last part is a little more difficult because you can't add or subtract 360s or 2 pi's to get on the chart of special values. So you just make an adjustment. So the identities that I'm referring to that cover this last adjustment are on page 146 in your textbook. One of them looks like this. One of them says the tangent of theta equals plus or minus, what do you think? The tangent of its reference angle, where you determine, use all students take calculus to determine whether it's plus or minus. And this doesn't have to be tangent. It can be sine, cosine, tangent, cosecant, secant, or cotangent. It's any of the 6 trig functions. This works. Okay. And that ends the lecture for this video segment. This is a very long video segment. It took about an hour and 25 minutes or so, an hour and 23 minutes. And I invite you to dig into homework right away. There's going to be a lot of homework on this section 2.4. Dig into homework right away, and I'm looking forward to talking with you all again soon.